Thank you for inviting me to do this talk. I've known many of you for years, in the case of Redler for 13 years, and every year it's when are you coming to EuroTcl. Well, this year I'm here and it's my privilege to be here, and I want to talk about some of the work that is done at the National Museum of Health and Medicine in Chicago. I'm a consultant to the museum. Last year I spent most of my time working on projects there. This year not so much, but it's fun stuff, and I hope to share with you the enthusiasm we have for what we're doing and show the place of TCL in making that possible. There are a number of... now I'm being trained, by the way. Steve Redler is training me to say TCL, not tickle, because TCL sounds more professional and business-like. But I'm still going to call them ticklers. There's a number of ticklers you may know about involved with the museum. Mike Doyle was the founder of the museum and benefactor. Cindy Lalagan, some of you know Cindy. Eric Tice, Steve Huntley is also involved. Steve's SEH on the Ticklers chat. Maury Pescatelli, Dave Roseman, and this gentleman sitting over here, Steve Redler. We've been doing a lot of work this year together on museum stuff, so let's start talking about some of it. I've got a video which I won't play because you won't hear it, but if you want to have a look later on, I'll show that. So, our main areas of research are in biomedical visualization and exhibition management, interactive digital exhibitions. And in particular, the juxtaposition of the two. I'm getting instructions from Tom Ashton. Now, if you look up here, those of you that went to the conference last year, this will be very familiar. I'm being told to move back. This isn't going to work. This is the exhibition space at the museum. For those that were there last year, you'll recognise it. And then on the right, you see some of the interactive digital exhibits. So let's have a look at the breadth of the research we conduct. One of the main areas is the AtLab system and the virtual microscope associated with it. These were donated to the museum, developed by EOS Technologies and donated to the museum, and then we're continuing with that research. I'll show you through these things in detail today. There's the National Museum of Health and Medicine Harvey collection, which contains the slides that were taken of Einstein's brain after his autopsy. And then I'll talk a little bit about the exhibit technology, and then the new stuff we're having fun with is 3D printing. And I'll try and run through a lot of this stuff quickly enough so that we can interrupt at any time, but we'll have lots of time to talk about the new stuff. Okay, so an AtLab, what is it? It is a web-based anatomical atlas. That means it's an atlas of human anatomy. Its client is written in the usual web technologies, but the content, images taken through a sectioned human cadaver. It's actually an executed prisoner. It's the quite famous visible human data set. The prisoner donated his body to science. After he was executed, he was snap frozen, and they ground him up. Grind off a millimetre. Who knows what a milling machine is? Okay, so you grind off a millimetre, take a photo of the end, grind off a millimetre, take a photo. So you end up with 1,728 sections, 1,871 sections, full colour. You'll see some of that. Now, if you're a little bit unsure about how you react to looking at sections through a human body, you're about to go into overload. The real cool thing about it is that the sections live on the web, and you look at this stuff through a browser. You don't have to bring it all onto your desktop. We've done the male. The female is currently being processed. The female image is currently being processed. And what makes it possible for this all to work is a thing called segmentation and annotation, which is basically identifying each structure in each segment. And I'll show you how that's done with the help of some TCL/TK programs. Bottom line is, in the male data set, there's lots and lots lots of images. There's 4,600 plus images. That's no, this isn't updated. 4,600 images. Where was I? So there's 4,600 images, of which 1,800 were the actual images across the body, and then we do them in other directions as well. Look, there's just lots of stuff. A total of nearly 700,000 individual annotations across all of those. And TCL/TK is extensively used in the back end. Extensively for the segmentation, the annotation, for image processing. The web server is the venerable TCL HTTPD. Data management indexing. All right. It's not updating. It should have been, sorry. And lots of data images. Equal backend. Here we go. So, this is what it looks like. I've got this standalone so I can run on my notebook later on. I want to have a look at running, but let's take some pictures. So we've got this navigation device here where we can select where we want to see in the body. That's what the blue line is. And who likes their beef red? And you can see that this is the section through there. Standard anatomical presentation. The subject on his back with his feet towards you. Okay, so you're looking. So that's the chest. That's the right side. That's the left side. So, it's set up to fit the browser, but we can also do it full size. And then the idea is you want to see what something is, you click on it. And so I've clicked on that, which is right lobe of the thyroid. It tells me that up there. It highlights it by using a coloured overlay, and then it just puts the box around it to show you where it is. This time oops. So that's the T1 vertebrae, and then big structures as well, like the deltoid muscle at the top of your arm. Now, if you look up here, that pink box is showing us the extent of the structure within the body. We can also click on that and turn the subject around so we can see the extent of it there. Put it back. We also have different types of renderings. This one was made by just stacking the sections up, and you're looking at the outside pixels, if you like. The really interesting thing is the guy had a dragon tat over his heart. Must have been a gang-related thing, I assume. So I took this up. It came out. We didn't want the dragon tattoo in the app, so I put it into the iPhoto app on the Mac and used the blemish remover to take the. And we can also do this translucent image here. Steve Huntley designed this one, and then basically it starts off as zero opacity, and the closer you get to the back, it becomes 100%. So you're sort of looking inside. And all these different views are useful if you're studying a particular piece of anatomy to get oriented in 3 space. And then a skeletal one. So we go back to there. Now the really cool thing is, even though the images are taken across the body, we are able to derive, this is the coronal section, so axial section is the way it was sectioned in the photograph. These are all derived, all done by TCL scripts driving NetPBM. And you can see where the blue line is, and that's the sagittal section, which is front to back. The other cool thing is you notice this, you notice this more button here. If you click on there, it shows you more information. And what that does at the moment is just hooks you out to Wikipedia. And as you click around on the left, on the actual image, this changes volume. So how is all this possible? How does it work with the, when you click on something, how does it know where you are? Well, that's a really cool piece of technology. So here we've got a section through the head. You can see up the top there going through. And you can see your head's mainly empty space. I know mine is. And that's your sinuses, the various sinuses. And think about it, if your head was solid, you'd be doing this all the time. So that's the ethmoid sinus. In fact, that's the anterior ethmoid sinus. I'm going to show you how we actually annotate that. I say we, I mean the experts in the field. So, this is a TCL-TK application. I think Cindy Lalagan was one of the main implementers of this one. And what happens is the people who are experts in anatomy sit down with this thing and they basically pixel paint the outline of the structure on top of the section. And there's code in there that does curve fitting. You see the little dots where they're outlining it. Code to curve fit it off the wiki. This is another one, the orbital gyri in the brain. You can see how they've outlined it. So once they outline the structure, we need to produce this pink overlay, which is a PNG translucent overlay to be put on the top of that. We also need to derive the dimensions for this box. And the other thing to note here is this is Windows and this is on Linux. So the previous one was on Linux. So the great thing with TCL-TK, of course, is it's cross-platform. So the annotators can use whatever they're familiar with. So the basic idea of the annotator software is it's TCL-TK based. It uses the IMG extension, uses SQLite for storage, and there's lots and lots of code from the wiki. I'll run through a few for you. Canvas item selections from Torsten Berg, color manipulation Jeff Hobbs, a little login dialogue from Richard Zuckenberg, simple zooming and scaling from Arjen Marcus, image scaling from Richard again, and drawing and editing. Canvas, I'm just seeing if there's anyone here whose work is used. Yes, canvas polygons from lines. Donald. Parsing CF. Anyway, basically a whole bunch of stuff off the wiki put together and make it possible. So, how does this work? How do we actually, when you click on that item, how does it decide that you're actually in that area there? Now, what we don't want to do is try and work out some sort of algorithm for checking if you're within the boundaries of a rather strange shape. The way it works, user clicks on that position, and we need to derive an index into the anatomical database, which will tell us the name of the structure, it will tell us the PNG file to load over the top. And how that works is a technique called Z-mapping, mapping from an XY position on a section to a 24-bit number that just happens to be our index into our anatomical database. And the way it works is we allocate a 24-bit number to each structure in the body. Okay, a 24-bit number. That 24-bit number just happens to be an RGB value. Not that we ever display it. Whoops, I did it again. And we create a secondary map. So in this case, you've got the section at the top, and there's the secondary map, and each structure is represented using its 24-bit value. This is on the client, this is on the server. This never gets to the client. But when the user clicks on a particular structure, the XY position is sent to the server. This is stored in a TIFF image. The server looks up the pixel color under that XY position, and it gets a 24-bit value. And that's the 24-bit value index into our database. So that's called Z-mapping. It's brilliant. Wish I thought of it. That structure, by the way, is the serratus anterior. I promised someone that he allowed me to do that. Now the problem was the actual code was written in 1995 to do that Z-mapping, and it was written in Java, and it was slow. So Steve Huntley pulled it to pieces, rewrote it in TCL in about 100 lines. It's faster, and we can maintain it. But that's the core of an app lab, is this Z-mapping technology. And of course the TCL is going to be great for manipulating TIFF images. So how do we create these ZMAP, how to create the TIFF images and then the overlays? Basically we've got four steps. We want to generate those TIFF images, the maps, then we want to generate the overlays, then we want to generate the bounds of the box, and then we want to validate the whole thing. So everything about it is huge. The data size, the time, the bandwidth just for transferring the results, because we host all of these things on cloud servers. There's 700,000 separate files to create, 9 gigs of ZMAP data to reference. So basically all your normal assumptions about building software, hardware, network, operating system reliability, they no longer apply. We've got to be prepared for spontaneous failures at every level in this process. And it takes about 2 days to do the whole thing. I went too far, sorry. And the way it's done basically is a bunch of TCL scripts and make files. And this combination of make to detect if we need to regenerate a file and then TCL to do the work makes it manageable. It still takes about 2 days. So let's look at each step in turn. So to create those TIFF maps, we transform from a polygon to a bitmap, the polygon on the annotation to a bitmap. I won't go into details, I'd rather show you the fun stuff later, but basically it's TCL. PNG overlays, they were interesting. Instead of reading pixels from compressed TCL files, it was reading lines. Imagine you've got a stack of these images, and so you're just going to read a line down, and then you just pick the ones you want in the plane you want, put them back together, and you end up with the image. Essentially, we were able to reuse code that was out there, which is another great benefit. I know I'm preaching to the choir about the benefits of TCL, but the other way of looking at it is this is reinforcing the message that you can give to the people who say, why do you use old technology? Because it works. It still required weeks, even to go from the set of the axial images to go to the sagittal and coronal. It still took weeks to happen, so we had to make it happen in parallel. And the annotators, the people doing the annotations, were relying on us to do all this processing, because then they could see if they made a mistake without lining the pixels as you went from section to section. So we had to turn it around quicker. Again, TCL plus make. So we spread the job over several processor boxes. We actually rented some Amazon, 8-core Amazon EC2 instances, and it took a couple of days. Steve, you heard the figure. How much an hour was that costing? Yeah, I know Steve mentioned it the other day. It gets confusing because we've got 3 Steves, so we refer to each other by our last name. The thing was, we were able to just take these cloud instances and do it. It only had to be done once. It took a couple of days, and I think we were paying $60 an hour or something. It was quite reasonable. So then we had another problem. They say if you've got a problem and then you decide to solve it in Java, you've got a problem factory. Well, if you've got a problem and you decide to solve it on the cloud, you've got a sysadmin problem, as well as your existing application problem. And this is where Fossil came in. What we're able to do is use Fossil as a transfer mechanism. Now, I know Richard spoke to you last year about Fossil. If you're not using it, I can highly recommend it. But we actually use it as a transport mechanism to get the content onto those virtual cloud servers. So all that happened is we pushed stuff into Fossil. At the other end on the virtual servers, it just did a Fossil update, and it brought across everything that had changed. So we got to the point where 3 8-processor virtual servers, complete set of overlays in 2 days, which is pretty good. And then we had to generate the offset information for the boxes. And again, that was just done. I wrote some image magic scripts and stuck those into the make file. So whilst it was doing all the other stuff, it was working out the boundaries and generated a little bit of tickle, which generated a lot of shell commands. It all worked. And the validation and quality control is an ongoing process. Just to reiterate, 700,000 separate files to create. And the real interesting, see, the thing is, if they change one little piece in one of those axial sections, let's say where they outline the structure and they realise they've missed a little bit, if they change that, everything has to change. Because that little pixel on one plane in that direction is going to affect everything on all the other, potentially every other plane. So we have to basically, it's an iterative process. Let the people who are experts in anatomy make their change, regenerate everything, then we have a look. See if they have a look and see what it looks like. 700,000 separate files, 9 gigs of data, and you're only allowed to take 8 painkillers a day. So TCL plus automation is a win. In fact, it made it practical. I don't think it would have been practical otherwise. So, the web server, the back end of all of this, TCL HTTPD. I think you're probably all familiar with it. We use direct domains to map to individual snippets of TCL code. It's single-threaded but with non-blocking operations. Did you know you can do actually suspend operations in TCL HTTPD? I didn't. Holden McCormack told me, oh yes, you can do that. It's not documented. You can actually suspend an operation in TCL HTTPD. So when you click on the XY position, it goes to the server. The TCL server is going to send a request. The web server is going to send a request to our ZMAP server, written in TCL with a separate process, which is going to look up which structure it is. Rather than block while it does that, the code suspends so that the TCL, single-threaded TCL server, web server, can then service other requests.
Are you using for that?
Are we using, sorry?
You?
No. This is all in TCL 7.4 compatible. They reckon, anyway. So if you use TCL HTTPD and you would like to know how to do that, pester me and I'll look it up. I don't remember offhand, but it's basically, you return from the direct domain function call, procedure call, return, and you give it a certain code, and that will suspend that particular call, and later on you can resume. It's kind of cool that it actually works. It's undocumented. So, single-threaded non-blocking. Back when, I think 4 or 5 years ago, I figured out how to do Ajax stuff in TCL, so we put that in. It's all Ajax support on the back end, which enables the front end to be modern web technology and just encodes in JSON and sends the stuff out. We've been experimenting with automatic segmentation, which is the process of outlining those structures. Segmentation is outlining them, annotation is giving them names. And we experimented with the ITK, the Insight Toolkit from the National Library of Medicine in the US. It has TCL bindings. In fact, Mike Doyle was on the grant committee that funded a project to do TCL bindings, but they're horrible. They were written in C++ using Swig, but it was a custom version of Swig to automatically generate the bindings. And the way it worked, it generated a TCL procedure for every permutation and combination of argument possible to the C++ function. So that added, that added 200,000 commands to the global namespace, where it put a number after each variant of the command. Totally impractical. So we engaged Miguel Safer to build a new binding, and he's back working on that at the moment. And the good thing is that with TCL is there's a near constant overhead on command dispatch. which means even if you do have 200,000 commands, TCL doesn't care, it's just you don't know what to call. So what Miguel is doing at the moment is writing an abstraction that's more ticklish, and that will actually generate permutation and combinations of C++ commands based on the arguments that you supply to it. So I'm hoping that he will be talking about that at the conference in New Orleans. So that's a work in progress. All right, now we get into the real fun stuff. So just to recap, Z mapping allows us to go from the XY on the plane to the structure. One day it occurred to me we could actually do the reverse. We could give it the structure, RGB value, and get it to build an overlay, which is like one of the axial sections containing just that structure. And then I realized I could actually give it a list of structures and end up with a series of sections containing just the structures we're interested in, just the parts of the body we're interested in. And then I realized, well, if I've got that, I can stack them up and ray trace them, and we could actually build some 3D reconstructions here. And that turns out to be a very practical thing for the annotators, the guys that are outlining, because if they can then see in 3D what they've outlined, they can tell if they've got it right. So the way that works, I use image magic to create a mask. So that's the effluent sinus again, and I specify the RGB values. Out of the TIFF file, I extract just the things I'm interested in, turn it into a negative, or invert it so that it's black with just white holes to show through. And if I put that on top of that, I get that. Or with the skull, I can do that. I just got a whole series of here that's just showing the skull. So the best thing is if I show you what it looks like. So this was, okay, I'm going to have to swap here. Just give me a moment. There's a button that says mirroring. Anyone know how to make this thing mirror? Okay. So this is one of the first ones I did, which was, you can see, is just the skeletal structure of the torso. The really cool thing about it is that is, the guy was, after he was executed, his family, I got all this off Wikipedia, so I don't have inside knowledge. But after he was executed, his family was given a couple of hours with him, and then he was snap frozen, and then sometime later sectioned. So these colours are real colour 2 hours post-mortem. And I can do this sort of thing. Now what I've rendered there is the diaphragm in situ. So you can see it tucked up under the rib cage there. And this is done by stacking up those sections containing just what I'm interested in and then ray tracing them. And I use a tool, interactive tool to do this called Osiris, which you can get for the Mac. And it's basically, it uses VTK, which is a TCL-based visual toolkit, and it uses ITK, the Insight toolkit underneath it. So it's a manual process, but nevertheless the results are quite spectacular. And this was used at the University of Illinois Medical School by Maureen Pistratelli, who's the anatomy professor and also a tickler. And he was able to use this stuff to teach. Let me show you another one. Everyone's gone quiet. Is anyone feeling uncomfortable looking at these things? So this is a similar one. Now, I didn't quite get the vertical axis right. And I've got to say, I'm a little bit nervous talking about 3D stuff and Paul sitting in the front row. Now, these are called object movies. That is, the viewpoint stays the same and the object's rotated. It's probably the inverse of what you do. No, you do a lot of this, don't you? But the other way of doing 3D is like you get the HTML5 virtual reality, where you've got a cube around you and the viewpoint stays and you warp everything around. These are object movies. We're looking at an object. And this gives you a real sense of where the diaphragm sits within the body. ago I had a rotator cuff repair on my shoulder, so I did this one so I could see what was happening. This is quite spectacular. You also see when you're on death row, you've got nothing better to do than work out. And that's, I believe that's the brachial plexus coming off the spine, collarbone there. That we can look up underneath. And these are just quick time virtual reality. We can put these out as a series of images and view it in an HTML-based browser as well, using a JavaScript library that just flips the images around.
Just missing the annotation.
And I suppose if I had the knowledge, I could use OpenGL and Toggle to do some of this stuff. We can also do, isolate things. And see this vertical line looks like a cut line across there? It is. The cadaver didn't fit in the machine, so they sectioned it, which means some of the data is missing. But that's a well-known problem with the visible human. This one is kind of cool because when you flip it up, you see I've left some of the musculature underneath. That's the adductor. I don't know. Got any questions while I'm doing this? This one I did for Halloween one year. All right. Now, one other one which Cindy was instrumental in was this one. So we left the skin on and made it translucent so you could actually see some structures in place. So this, I believe, is an artery, and that's a nerve running down there. All I know is when the anatomy people saw this, they went absolutely wild. It's like porn to them. I don't quite see it myself, but it's kind of cool that we can do this stuff, and you are actually looking at real human specimen. I mean, we're mindful of the fact we are dealing with human remains even digitally, so you've got to be respectful, but this is kind of cool. All right, I've got lots and lots of this stuff I can show you. I won't bore you with too much more. I'll give you a fly-through movie. This is a kidney. And this stuff's all based on those section images that are taken across the body. And just because they are annotated, because we have that great big database saying what everything is, because of Z-mapping, we can work backwards to get this stuff. All right. Well, that was exciting. Oh yeah, time's good too. So I'll redo this, go back off that.
Have you thought
Yeah.
Have you thought about adding annotation to the 3D images as well?
Oh yeah, we can.
We're going back through the
Reverse.
Yeah. Reverse to reverse it.
Reverse to reversing. Have I got one here?
Steve, and can you show also? Oh, this one.
Yeah.
That's nice.
So this one I think has annotations on it, but only every so many images and they pop up as you rotate. I'm not sure. That's this one is the